Welcome back. In today's video, I'm going to show you a few examples of how to apply the integrability condition to see if a vector field is a gradient field. We'll start with the vector field in the plane. So V is defined on R2. And V of x1, x2 is just minus x2 and x1. Let's check the integrability conditions to see if this vector field here can have a potential. We have two coordinates here, v1, v2. So we need to check the mix. Basically, there's only one possible mixed derivative that we have to check. That is dv1 with respect to dx2 and dv2 with respect to dx1. So let's compute that. dv1 with respect to dx2x. v1 is this minus x2, this coordinate here. And if we take the partial derivative with respect to x2, what we get is minus 1. And we need to compare this with dv2 dx1. So we need to take the derivative of this coordinate here with respect to x1. And the result here is obviously plus 1. So what you can see is these two do not agree, and that means the integrability conditions are not satisfied. So V is not a gradient field. And we don't even have to check whether the domain is simply connected or not. Okay, for our second example, let's take a look at something similar. Let's take the vector field V defined on R2 again. That maps x1, x2 to simply x1, x2. Again, let's check the integrability conditions first. And again, we take dv1 and differentiate it with respect to x2. So this is this coordinate. If we differentiate that with respect to x2, then well, there is no x2 in that expression, so the result is 0. And we need to compare that with dv2 dx1. So this coordinate here, there's no x1 in that coordinate, so again, the partial derivative of that with respect to x1 is 0. And that means these two expressions do agree. So that means integrability conditions are satisfied. So it can still be a vector field, a gradient field. What we need to check as well is simple connectedness of the domain. So the question is the domain simply connected? The domain in this case, if I didn't specify the domain, then I always mean the maximum possible domain. So that is R2 in this case. And R2 is, of course, simply connected. No holes in that. So that means V is a gradient field. I didn't ask for the potential, but of course you're welcome to try and find that for yourself. Shouldn't be too complicated. Meanwhile, let's have a look at a third example. We'll consider a slight variation of one of the vector fields that we have already seen. Again, we consider the vector field minus x2, x1, but now we modify that a little. We modify it by adding the factor 1 over x1 squared plus x2 squared. So we divide by the norm of x squared. Okay, so this is kind of a normalized version of our first example. Again, let's have a look at integrability conditions, how these change. You will remember that those were not satisfied with the first example. So let's compute them again. Let's see, dv1 with respect to dx2 of x. So we need to differentiate that first coordinate. And that is now minus x2 over x1 squared plus x2 squared. So let's apply quotient rule to do that. So we need to take the derivative of minus x2 first, that is minus 1. We multiply that with the denominator, x1 squared plus x2 squared. And then we subtract minus x2, so we add plus x2 times the derivative of the denominator with respect to x2, that is 2x2. And that all needs to be divided by the denominator squared. Okay, so if we simplify this a little, we can see that we have x2 squared with a minus in front of it here, minus x2 squared, and here we have plus 2x2 squared. So that means what we get is plus x2 squared, and also we keep the minus x1 squared, of course. Okay, so the whole expression becomes minus x1 squared plus x2 squared over x1 squared plus x2 squared squared. So let's compare that with dv2 dx1. That is similar but not quite the same. So we have this expression x1 over x1 squared plus x2 squared. We need to differentiate that. And again, we apply quotient rule. So we start by differentiating the x1. The derivative of that is 1. And we multiply this with the denominator. And then we subtract the derivative of the denominator times x1. So here we have x1, and the derivative of the denominator is 2x1. And again, we need to divide that by x1 squared plus x2 squared squared. And what we get is, well, here we have minus 2x1 squared. And here we have x1 squared plus x2 squared. So we get minus x1 squared plus x2 squared over x1 squared plus x2 squared squared. So what we can see here is, in the result, these two expressions here, those coincide. That's the same value. So those are equal. And that means the integrability conditions are now satisfied. Okay, so with this little change, we get a vector field that does satisfy the integrability conditions. So what about simple connectedness? Of our domain? Well, what is the domain in this case? Again, it's R2, but we have to exclude one point if you look back at the vector field here. The one point that we cannot use here is the origin, because this expression is not defined if both x1 and x2 are 0. So we have to exclude the origin from our set here. And that means we punch out a single point. So every curve around that point cannot be contracted to a single point anymore, right? And that point has to be also contained in the domain. And that means that set is not simply connected. Okay, so that means our theorem does not apply. And we cannot possibly say whether this vector field V is a gradient field or not. Okay, so it's unclear whether V is a gradient field or not. It could still be, because it does satisfy integrability conditions, but we cannot use the theorem because our domain is not simply connected. Right? So, of course, for subsets of this R2 without the origin, subsets that do not contain this hole in the middle, we do have a simply connected domain. So on these subdomains, our vector field would be a gradient field. It's not clear, however, whether that also applies to that field. And if you do the math, if you try to actually compute the potential, then you will run into troubles, and you should find out that this is not actually a gradient field. But the theorem itself does not tell us that. Okay, so let's also remark that. If we restrict the domain such that it does not encompass that hole, at 0, 0, then the vector field has a potential. So for example, let's say if we define D to be all x1, x2 in R2, where let's just say both x1 and x2 are strictly positive. So we take the positive quadrant. Then we have a simply connected domain. And so that means V is a gradient field over D. So for those partial domains, we can find potentials, but maybe there is no potential, and there is no potential that covers all of R2 without our origin, without the hole. And again, the theorem does not tell us whether there is a potential or not. The theorem cannot be applied because the domain is not simply connected. That's the catch here. Okay, one last example that shows us how to do that in dimension 3. So let's take a vector field defined on R3, where v x1, x2, x3 is, let's say, e to the x1 times x2 plus 1, e to the x1 plus x3 and x2. So that's a little more complicated even. Then let's have a look at the integrability conditions. And unsurprisingly, there's some more work to do right now. So first, let's start with dv1 dx2 of x. So we differentiate the first coordinate, this expression here, with respect to x2. x2 only appears here, so what we get is e to the x1. On the other hand, dv2 dx1 of x, so this expression here, if we differentiate that with respect to x1, that only appears here, then we also get e to the x1. So that is satisfied for this pair. Now for the other pairs, let's see, what else do we have? We also have, for example, dv1 with respect to dx3. There's no x3 in v1, so that is simply 0. And we need to compare that with dv3 dx1. And also this is dv3. There's no x1 in here, so this is also 0. So again, that pair also satisfies the integrability condition. And let's see, we're missing dv2. We already did dv2 with respect to dx1. That's in here. So, but we're missing dv2 with respect to dx3. So let's have a look at that. This is v2. Here's an x3 in there. So the derivative of that is 1. And then we need to compare this with dv3 dx2. So if we differentiate that with respect to x2, we also get 1. And that means those two also agree. So dv2, we already did dv2 dx1, we did dv2 dx3. So what about dv3? We did dv3 dx1 and also dv3 dx2. So we're done. That's all the conditions that we have to check. And that means integrability conditions are actually satisfied. Okay, so what remains to check is simple connectedness of the domain. The domain, you will remember, is simply R3 here. The domain is R3, which is simply connected. And that means our theorem does apply. So V is indeed a gradient field. And again, you're invited to try and find the potential for yourself. Okay, this concludes the examples. I'll see you in the upcoming videos. Bye.